This is the video that goes with Lab 14 in your packet, Charles Law. From this packet, I would like you to complete all of the pre-lab questions. In the video, we're going to collect the data and then you'll do the calculations. If you get stuck, you can always reach out to me or maybe to some of your classmates. And then I'm only going to have you answer some of the reflective questions. The ones I would like you to complete are questions 1, 2, 3, and 7. Now, before we start talking specifically about the lab, I'd like to talk about how I would like you to submit the lab. So once you've completed the sections that I've asked for, you can scan your pages and save it as a PDF file and upload it in the Charles Law assignment in Canvas. Or if you don't have a scanner that you have access to, another alternative would be to download on your phone or tablet a scanner app. I've used a Scanner Pro, which is a free app, and it takes a picture of your pages and then it will convert it to a PDF file, which then you can easily upload into the Charles Law lab assignment in Canvas. If you don't have any access to a way to make your pages into a PDF file, as an alternative, you could retype the answers to your pre-lab questions, your data, your calculations, and your post-lab questions or reflective exercises in a Word document, save the Word document, and upload the Word document into the assignment in Canvas. I do not want you using just simply pictures. They do not always come through very well, and so then it makes it very difficult for me to review the work that you've done. So either a PDF file or a Word document would be acceptable formats to upload into the assignment in Canvas. So let's talk a little bit about Charles Law before we look at the data. So gases can be described with 4 properties: pressure, which is they use a capital P, a volume, capital V, temperature, capital T, and then the amount, which is an N. So a gas is described by these 4 properties. But oftentimes, gas laws look at the relationships of 2 or more of the properties to each other, and to do that, they have to hold some of the properties constant. So Charles Law looks at volume and temperature and their relationship when they hold pressure and the amount constant. The pressure for this system will be the atmospheric pressure, so that is held constant. And then when we look at the setup, you'll see how they manage to keep the volume of the gas constant in the setup. Or not the volume. That's an incorrect characterization. They keep the amount of the gas. No gas can get in and out. The same amount of gas has to stay there. Sorry. So we're looking at volume and temperature together for Charles Law. And volume and temperature have a direct relationship. So we would say volume and temperature are directly proportional. So this is a language that they use a lot when they're describing the relationship between 2 variables. And when something's directly proportional, it means that those variables change in the same way. So if one of them increases, the other would increase. So that's the same, both increasing. Or if one of them decreases, then the other would decrease. So again, that's the same, both decreasing. So directly proportional means they'll change, increase or decrease in the same way. The opposite of directly proportional would be inversely proportional. And if something's inversely proportional, then when one thing increases, the other would do the opposite and decrease. For more discussion on directly and indirectly proportional, you can look at some of the videos in gas laws. So Charles' law is written as the relationship between volume and temperature. So it's a direct relationship, and so mathematically it looks like this. That's the relationship. And we're going to look at how when you change these properties, what happens. So we're going to start with an initial volume, volume 1, and an initial temperature, temperature 2. And we're going to see what happens to it when we change the temperature, is what we're going to change. What happens to the volume? So we have a new volume and a new temperature. Now it's worth noting at this juncture that for all gas laws, the temperature must be in Kelvin. And so where this causes a little bit of trouble is in lab we measure in Celsius. And if you calculate using your Celsius, even if you do all the mathematics correctly, you'll get the wrong answer. So before you do anything in gas laws, be sure your temperature is in Kelvin by adding 273 to your Celsius temperature. Specifically, it's 273.15. But if you do 273, your calculation should be fine. So remember, temperature must be in Kelvin. Now for this lab, you're going to make measurements of the initial volume, the initial temperature, the final volume, and the final temperature. And how we're going to determine if or verify Charles' law is by mathematically rearranging. So we're going to cross multiply. And so we'll have volume 1 times temperature 2. And then it would be over temperature 1 times volume 2. And if we get all the variables on the left-hand side, then it should equal 1. So how we'll verify Charles' law is we're going to measure volume 1, temperature 1, volume 2, temperature 2. So we're going to measure all of these things. And then you're going to plug them into this equation and see how close you get to the number 1. So let's go ahead and look at what I did in the experiment. I know these pictures are not gigantic, but hopefully they're big enough for you to get an idea about what's happening. If you don't already have your procedure out and your data page out, take a few seconds now and get your procedure so you can follow along and get your data page so you're ready to record your data. So on this particular part, verifying Charles' law. So what we're going to do is we get what they call an apparatus. And if you read through this, they talk about a needle and a septum. Well, the college wouldn't let us use needles, so we had to modify our system a little bit. So this is a picture right here. I'll label this number 1. This is our apparatus. It has a flask. So there's the flask. And then it does have an arm that goes to tubing. So instead of having a needle going in the top, our gas will go in and out of the tubing. And then down here is a stopper. And we're going to put the stopper, once we get going, the stopper goes into the flask. And so we call this apparatus our experimental chamber. So when it refers to the experimental chamber, this is what it's referring to. So there's step 1. So step 2, it says on the outside of the tube, on the outside of this experimental chamber, take a wax pencil. I used a Sharpie and mark how far the stopper goes down. So I took a Sharpie and just put a little mark on the neck of the flask. And then here, this is actually steps 3 through 5 in this picture. And this is what the overall setup looks like in this bottom picture. So I have a flask with water here on a hot plate. Here's my hot plate. Here's the experimental chamber above the water at this point. And then the tubing is going down into a flask with water, which I actually, the directions hadn't told me to set it up when I took this picture, but I had it already set up. So then step 6 says, while your water bath is heating up, prepare an ice water bath. So this is step 6. Got an ice water bath. It's all ready. And then step 7 is here. And this is the flask that I was showing you in the other one. I'm going to look back there again in just a minute. And so this tube right here is coming from my experimental chamber. I put about 200 milliliters of water into the experimental chamber. Notice it's open, and the only important thing here is that I leave the tube underneath the water. Now, they call this flask, so the language, the reservoir. So this right here is the reservoir. Now let me go back, and I'm going to erase the marks that I had on this so you can see the whole setup. So what I have here, this right here, there's the experimental chamber. And then right over here with the tube under the water, this is the reservoir. So that's how it's set up. Now it says, step 8, place it in the reservoir. And so that this is step 8, is making sure that it's under the water. Now then step 9, this is where we're going to record our measurements. If I could spell record. So it's at this point it says your boiling water should be boiling, and it was, and your ice water should be equilibrated, and it was. And so we're going to record, this is our first piece of data, this picture right here. This shows my boiling water bath. So record that temperature, and this shows the ice water bath. So record that temperature. Now our thermometers, the lines are 1 degree, and so you'll estimate to the tenths place. So you should have one decimal. So like 85.3. So 1 in the hundredths place, 1 decimal. Okay, so now you should have 2 numbers, the first 2 numbers in your data. These are our thermometers are degrees Celsius. Then step 10, lower the clamp holding the chamber, and we lower this chamber. There's the experimental chamber right here, experimental chamber, and I've lowered it into boiling water. And this down here, here's the reservoir. They tell you it's very, very important that you don't allow that tubing to come out. And what happens is the gas, there's air inside of this experimental chamber. As it heats up, the air expands and the air goes down this tube, and we see bubbles. Now, here's one question that you may have already encountered as you're thinking about this. The gas we're using is air. And air is a mixture of gases. And so why don't we have to worry about that? And the reason is gases are very, very far apart. And so we assume that there's so much space that they don't really have a lot of attractive forces with each other. And so when they behave, pure gases and mixtures actually behave in similar ways. Again, because they're so far apart and they don't have the strong attractive forces between them. So we're testing out Charles' law with air, but it would be something similar if we had a pure gas, just like oxygen. Now, so once this all bubbles, eventually it stops bubbling. And once it stops bubbling in step 11, so this is step 10, and then once it stops bubbling in step 11, they want us to put it into the ice bath. So now here, this is ice bath. And up here, it's a boiling water bath. And so now we cool it down. And so the air here, our chamber is inside here. And what happens is when you cool it down, the air contracts and the water, the air is like sucking it into the chamber. So the water comes in here and we get a little bit of water, which you'll see in the next one. So what I observe here in step 10, I observe bubbles coming out as the gas expands. And as in step 11, I see water going into the experimental chamber as the gas contracts. I also could see that this water, the level was going down because the water was going in here. No measurements here, just observations. Measurements on the next page. All right, so then it says step 12, when the water no longer flows into the experimental chamber, take it out of the ice water bath and remove it and immediately cap the needle. Okay, I didn't have to do that. So here is step 12. So you see that the tubing is still, this is my reservoir. But now look here, do you see the water? There's water right there. I'll erase it so you can see. There's water in there. So that was drawn into it. So then what it says is remove the stopper and use a graduated cylinder to measure the volume. Now here we go. Record this value, which will be called VW in your calculations. So this is this is our experimental chamber here. So this is the volume of water in experimental chamber. So I took it here, I poured it into the graduated cylinder, and this is what you're going to measure. Remember, you're going to look at the meniscus, and again, this graduated cylinder has lines to the ones place. This is a 10. It's hard to see, but this is a 10. And this line right here, this is 20 right there. That's 20. And so you're going to measure the water. I'm going to erase the line that I drew for the 20. But the 20, so you can see, there's the 20 right there. So there's another line right here. Oops, sorry. There's 21. And this is 22. Oh, my pen is messing up. So there's 21. Oh gosh, sorry. My pen is not making a good mark. Okay, let me erase it because I think it'll be easier for you to read. Okay, so you're going to record this as the volume of water in experimental chamber, and the directions tell you this is VW right here. Then step 14, which the pictures are the next one, it says determine the total volume of the experimental chamber by filling it to the line and then using a graduated cylinder, and this is VEC. Okay, I had it two places, so that's good. So step 14. Determine the total volume of the experimental chamber by filling it with water. So here I show you, here's a picture, and I filled it up to the mark. Now notice I had to take a clamp right here because we didn't have the needle. So if I would have left this open, the water goes flowing out. So this right here is just a clamp to make sure the water stays in the chamber. And then I filled it up. This was a very, very big graduated cylinder. And so now on this is step 14, and we're going to record this. And this is the volume of the experimental chamber. So this is the total volume, not the volume of water, the volume of the experimental chamber, and it's going to be called VEC. Now, what I need you to notice on this one, this is a very big graduated cylinder. Notice this number up here is 170, and this number here is 150. The water is right around just above this. Now the 150 line is right here. I'm going to erase this in a minute. So if you look, this actually goes up by twos. So this is like 150, 152, 154, 156, 158, 160. So it's going up by twos. So when you record this volume, you will only be able to go to the ones place, right? So you might get 151, 155, 154. You won't be able to have a decimal place on this graduated cylinder. Now I'm going to erase this again. You can go back and listen again if you need to understand it better, but I think that seeing the lines might be a little more helpful. So now you're going to record that volume. Okay, so now you have all the data filled out. Okay, so you have the temperature of the boiling water bath, the temperature of the ice water. You have some observations as the experimental chamber cools. You should have the volume of the water in the experimental chamber and the volume of the experimental chamber. So that's all the data. So how does this translate? And I think it will all help you. So when you look in the calculation sections, the initial temperature is going to equal the temperature of the boiling water bath. Now, if you're looking in your data, step 15, you can reread it, that in your procedure, that tells you this. Okay, and then it says the final temperature, so T final, they use, instead of 1 and 2, they use I and F, which is okay. Initial would be 1 and final would be 2. The final temperature of the air in Kelvin, this is going to equal the temperature of the ice water. Now you might think, well, why? We're measuring water, that's not air. But remember, we set our chamber into that water, and so the air inside the chamber became the same temperature. Now, notice the calculation you have to put into Kelvin. Maybe I'll write that in red so you don't forget. Convert to Kelvin. Okay, so and again, you can look in your procedure on step 15. It tells you this. Now, then look at step 16. In the procedure, it's going to help you out with your calculations. It says record and calculate the initial volume and the final volume. Okay. Then if you look, it says on step 16, look with me, determination of VI. Okay, V initial. When the experimental chamber was in the hot water bath, the air expanded completely to fill the chamber. Any air that exceeded the volume of the chamber escaped into the reservoir. Thus, the initial volume of air in the experimental chamber is equal to the volume of the total volume of the experimental chamber. So the initial volume is equal to the volume of the experimental chamber. Then it tells me the final volume, and you can read along with me. When the experimental chamber was placed in the ice water bath, the air contracted and the water filled in the empty space. The experimental chamber. Thus, the volume of the air in the experimental chamber when it was in the ice bath, VF, equals the difference between the total volume and the volume of water in the flask. So the volume of the EC minus the volume of the W equals the final volume. Okay, so that tells you in step 16 what you're going to have to do to figure out the initial volume and the final volume. And then finally, to verify Charles' law, you're going to plug in the data that you just determined, and you're going to plug it into what we had before. So you'll say V initial over T initial, then times T final, V final, and you're going to find the answer. Now, I would say from my experience, and I have not plugged in the numbers that I got from your lab, but that number in general is somewhere between 0.8 and 1, the answer that you get here. And then finally, the deviation, you'll use equation 3, which is in your book on page 203, to figure out the percent deviation. So what I would like to do is let you try, give it a shot. If you have questions, let me know. I know I did not do a specific example. That's because I want you to try first. If you have any trouble, please let me know, and I will do my very best to help you work through it. Good luck.